So here's the analysis of the standing wave that we just saw. I said you should do it yourself, but I'm going to go ahead and show you. If I have my two single frequency waves, and indeed that's a wave that travels in the plus x direction with a speed of omega over k, and indeed this is a wave that travels in the minus x direction with a same speed, omega over k, but they also both have the same frequency. That's what gives us the standing wave. Let's go ahead and plug that into the sum. I haven't done, this is the sum, and that means that the average k average is equal to k1 plus k2 over 2 is k, omega average is 0, and delta k over 2 is 0, and delta omega over 2 is omega. And so what we're left with is the sum psi1 plus psi2 equals a sine of kx times the cosine of minus omega t. So what does that tell us? Well, first of all, the phase velocity, v phase, which equals omega average over k average, is equal to 0, and the group velocity, v group, which is delta omega over delta k, is undefined. Right? So the fact that there is an envelope term is just that the group velocity is undefined. What that does is it gives us just a time dependence but no spatial dependence. Notice the spatial dependence is gone in the envelope term. Spatial dependence is gone in the envelope term. And the oscillating term, right? So it's just a simple sine kx. It has no time dependence. So what does the envelope term do? Right, so this is the oscillating term. So that's the wiggle that you see, right? That's the oscillating term. And the time dependence, the envelope term, what that does is there is no envelope. So what it does is it simply modulates the oscillating term. It makes it bigger and smaller as time goes on. So the oscillating term gets bigger and smaller as time goes on. So none of the peaks actually move anywhere. They just get bigger and smaller. That's a standing wave. I think that's pretty cool.